For most of the 19th century, electricity and magnetism occupied separate worlds. A spark jumping between copper wires had no physical relationship to a compass. In 1830, Michael Faraday began a series of experiments in England that started to erode that distinction. He discovered that moving a magnet near a coil of wire could generate a measurable electric current. At the same time, Joseph Henry recorded the same result in the United States. Two scientists, working oceans apart, had identified a consistent physical link between these two forces. But the link is specific. Simply holding a magnet near a wire does not produce electricity. The field can be massive, but the wire remains dead until a specific change occurs. To understand how we generate power today, we have to look past the magnet itself and quantify a new property, magnetic flux. Imagine a uniform magnetic field as a directional stream of force flowing through space. To measure its impact, we define a specific window, a flat surface that this invisible stream passes through. We track this using an area vector, an arrow sitting perfectly perpendicular to a surface, identifying exactly which way it faces. Magnetic flux is the total number of field lines that physically pierce through the boundaries of that specific surface. Because of this, the physical orientation of the window matters. If the surface tilts, it catches fewer field lines. The flux changes even if the magnet generating the field stays perfectly still. Calculating flux requires three variables: the strength of the magnetic field, the size of the surface area, and the angle theta between them. Mathematically, flux is the dot product of the magnetic field and the area. This means the value peaks when the field and area vector are aligned and drops as they move out of sync. This relationship is expressed through a specific equation. Flux equals the magnetic field strength times the area times the cosine of the angle between them. That cosine value scales the total flux based on how much the surface is tilted. We measure the final result in Webers. 1 Weber represents the standard unit of magnetic flux, equivalent to 1 Tesla meter squared. This equation describes an ideal scenario where the surface is perfectly flat and the field is completely uniform. However, real-world physics often requires a more granular approach. In a laboratory, we can use flat surfaces and straight fields, but the real world is built on curves and irregular magnetic gradients that shift in strength from one point to the next. On a warped surface, theta and field strength differ at every coordinate, making simple calculation impossible. The solution is dividing the surface into microscopic squares called area elements. Each element acts as a perfectly flat surface with its own local area vector. We calculate flux for each tiny square individually, and then use summation, adding every small piece together to find the total flux for the entire object. By breaking a complex geometry down into small, simple pieces, we can measure the magnetic flux through any object, regardless of its shape. When a surface is rotated so it sits parallel to the magnetic field, the field lines slide past the window without crossing it. The angle between the field and area vector reaches 90 degrees, and flux drops to 0. If the surface rotates to face the field head-on, the angle returns to 0. The maximum number of field lines pierce the window, reaching peak flux. In most machines, we don't change the magnet or the size of the wire loop. We generate change by constantly rotating the loop, shifting that angle theta back and forth. This explains why Faraday saw a current only when pushing a bar magnet toward a wire coil. He was changing the environment of the wire in real time. As the magnet moves closer, the number of field lines piercing the loop increases. The flux counter rises because the field is becoming more dense within the area of the wire. It is this change, the time rate of change in magnetic flux, that generates the electric currents used by modern civilization. Without a changing flux, there is no induction.